Welcome back, guys. In the previous lecture, we implemented call to the function printf, right, which is our external function. And today we'll start talking about parsing. That is, we'll start accepting our programs. And we're going to implement exactly the same call to the function print, that is printf, passing our string, right, such as hello world. And in general, we said printf accepts multiple arguments, right? That is, we can pass the format string in using format characters, right, such as %d for numbers, and we can pass the value 42. So as the result of today's lecture, we should see this value printed. But let's start from the parser. As we said, we'll be using the S-expression format for our programs. And we actually implemented the parser for S-expression in C++ in the class called building a virtual machine. So I'm going to delegate to that lecture, and then we'll get back to integrating parser. Right, for this we create the BNF grammar. And as previously, we're going to use syntax tool, that is the syntax CLI module, which, as we can see, accepts the grammar. So let's switch to the lecture to build the parser. Now, syntax tool is distributed as the syntax CLI module in NPM, and NPM is the package manager for Node.js. So this is how to install it. NPM install, passing G parameter for global, and specifying the packet name, syntax CLI. So EVA programming language will be following S expression, that is the either simple atoms such as numbers or symbols or strings, or lists. It might be empty list or a list containing some other sub-expressions. And as we know, first we define the lexical grammar, that is the tokens. So let's start from skipping the white space. Right, if we met the white space, we just return the empty token type. And this is the sign for syntax to just skip it altogether. Then let's have the numbers, and for now let's use just simple numbers, /d+, that is digit repeated one or more times. The strings will be anything in double quotes. And also symbols, here's the regular expression for symbols. And let's also support the comments, single line comment and multi-line comment, also going to skip them, similar to the white space. That's pretty much it for the lexical grammar. Again, if you need to have details on parsing, please address two courses, Building a Parser from Scratch or Essentials of Parsing, where we discuss in detail what is lexical grammar, syntactic grammar, etc. And now let's define the syntactic grammar, that is the BNF, in Bacchus-Naur form. So previously in JavaScript, we've been using just the JavaScript arrays to hold S-expression values. This C++ is a lower level language, and that list or array may contain any values. In C++, to achieve this, we'll need to define an expression type. So as we said, we support numbers, strings, symbols, and lists. And the expression itself contains the expression type and data fields corresponding to the type. In this case, we don't use the union, otherwise it will be more complex handling for the strings and vectors. But this is exactly how we're going to represent an AST node. It has a type and specific data fields. Let's introduce convenient constructors. So one for number, and set the number field. Now, if we receive the string in the constructor, then we need to check whether the first symbol is the double quote, and in this case we set the type to string, and the data, that is the string field, contains the value between the string quotation, right? We strip the quotes. Otherwise, it's just the symbol, that is the variable name, and we set the type to the symbol. In this case, the actual value is taken as is. And finally, if we receive the complex list, that is the vector of expressions, we set the type to the list and the appropriate list member. Now, the C++ plugin for the syntax tool expects the final result to have the value type. So we're just using the type alias and say that the value, which is used by syntax, is the expression. And this is exactly the type of the AST node. Okay, so these are just helper data structures. And now let's define the actual grammar. Now, the expression production, as we said, is either a atom or a list. Again, atoms are simple numbers, strings, and symbols, and lists are nested lists. And now let's define what is atom. It's either a number, right? This number in uppercase comes from the tokenizer. In this case, the result is the AST node, that is the expression instance, passing the number. Right? For this, we use the number conversion. And as you can see, it's just integer numbers as an exercise, and to do, please consider adding the double numbers here, right, with the fraction point, updating the regular expression, and converting to double. It's either a string, and in this case we pass the captured token as is. It might contain quotes or might not, and our constructor handles this. Or it's a symbol. And in this case, we also pass the token as is. And the list consists of group in parentheses, inside of which we have list entries. And the list entries might be empty for empty lists. But as the result for the list production, we return exactly the list entries. That is the actual vector. So let's define quickly list entries. It's either empty as we said, and in this case we just allocate an empty vector, and otherwise it is recursive production, list entries followed by expression. So we can substitute for this list entries anything from list entries, including itself, and this is how we get expression followed by expression followed by expression, etc. In this case we push the final expression, that is the $2, into the list, which by this time is allocated, and the result is the final entries list, that is the $1. Again, if you need more context on parsing and the parser generators and the grammars, please address the Essentials of Parsing class. Okay, let's try generating our parser. Right, for this we call the syntax CLI passing the grammar. We specify the mode as LA-LR1, which is the most practical in this case. And we specify the output, which will be the header for the eval parser, right, evalparser.h. And as you can see, syntax tells successfully generated. If we open that generated file, we really see here's our expression type, followed by generated code for the tokenizer and the parser. Okay, sounds good. Now when we have parser, we can include it and start using. Right, so we implement in the first step, passing the string program to the parser and obtaining the AST. And for this, we can also pass the AST to our compile method. Okay, include the parser.h, and let's also define the parser instance on our compiler, also unique pointer, and initialize it in our constructor. Let's make unique eval parser. Okay, so that should work. Let's get back to our compile method. Right now we can start accepting ASTs. Now remember the type of the AST nodes from the eval parser is exp, that is expression. So we accept the reference to the whole AST in the compile method and pass it down to the gen method. And let's start handling different expression types. So first of all, for simple numbers, right, we're going to do exactly the same. Get int 32, we pass expression.number, that is the specific number. The next step is strings. Right, exactly the same. We call create global string pointer, passing the actual string from our program. Now we also have symbols, such as variables, operators, which we will handle in the next lectures. And today we'll handle only the function printf, that is called to the function printf, which is the final expression type, that is lists, where the first element, that is type tag, might be of different types. So if the operator, that is the type tag, is printf, we treat it specially as the call to the function. So we port everything from our previous implementation, that is getting the function printf, allocating arguments, and creating the call expression. Now, in contrast with previous case, in addition to the format string, we need to handle all the arguments, right? Not just the first argument. Now, for this, we go through the rest of the expressions in the printf call, right? With this, we'll get the format string, the number 42, and anything else, and just call recursively gen function, right? Passing the specific expression type. And finally, we have the same create call, passing the printf and the arguments. Sounds good. Let's have the default value at the very end of the gen function and just return 0. And that should be it. Let's try it. Okay, some errors. Okay, we need to import the eval parser from the syntax and also have the typo parser parse. Okay, so that should be it. Let's try executing. And there we go. We see we handled all the compiled expressions, right? We see the numbers, the strings. But take a look, instead of value 42, we see some value 420. Well, in fact, we have value 42 and then there's no new line at the end. And then we have the 0 result as a result of our compilation. So let's add new line. But unfortunately, as you can see, it's not handled here. So we need to update either the parser or unescape those new lines and special characters when we handle the strings. For now, let's do this inside the string itself, just using the regular expressions to unescape. And I'm leaving to do to handle all the characters, not just new lines. Or you can handle also at the parse level. And for this, we need the regex module. Okay, sounds good. Let's try again. And it works. Again, as you can see, our value string is saved automatically into global variable. And exactly the same, we can just have the string, for example, hello, And as we can see, it's also saved to a variable. So in the next lectures, we'll actually start talking about variables, specifically about global variables first, and going down to local variables, stack frames, blocks, etc. That's it for today. Thanks and see you in the class.